So lesson 3.3, today we're going to look at equivalent equations and basically going to focus on solving these equations, just kind of reinforcing some skills that you should already have. And we should just know that if we perform the same operation on both sides of the equation, it maintains the fact that it's equal, that it's equivalent on both sides. And so we're allowed to subtract on both sides, add on both sides, multiply on both sides, divide on both sides, as long as you do the same thing on both. Okay, and that will create an equation that is easier to solve. So first of all, equivalent equations have the same exact solution. So if we're going to look at two equations, and again, equations being different from expressions because equations have an equal sign and expressions are just a number sentence. We're going to look at two equations, and we're going to say that they're equivalent equations if they have the same exact solution. So let's look at these two. 2x plus 5 equals 11, an equation, and 2x equals 6, an equation. Are they equivalent? Okay, so what we want to do is we want to solve for both of them and see what the answer is. So starting with 2x plus 5 equals 11. Now, the last couple of sections, we've been using those triangles with the facts inside and stuff, but we want to kind of go to the most efficient way to solving these equations. And so the most efficient way is to add and subtract, multiply and divide on both sides to basically simplify what we're looking at. And our final goal is always to get x by itself because that's a solution. X equals something. And so in order to do that, we talk about eliminating things that are on the same side of the equal sign as x, so that everything ends up on the right and then simplifies to a single number. So that's the value that x is. So going back to basic two-step equations, we're going to save the division for last. Now we will start to look at some times where you can divide first. We can technically divide by 2 if we wanted to right now, but you have to divide everything by 2, including the 5, including the 11. And if you just think about what that's going to do, that's going to make some nasty decimals. So usually we don't divide first because it produces some decimals that we don't want. So it's always easier to subtract. So we're going to subtract 5. If you remember back to middle school, and those that weren't in middle school with us, we used to draw a little dotted line here, and we had to make sure if we did something on the left side of it, we also did it on the right. So the dividing line is the equal sign. And the reason you're allowed to do that is because if you have 10 equals 10, if you add 5 to both sides, it now says 15 equals 15, which is still true. So as long as you do the same thing on both sides, times 2 times 2, 30 equals 30. It maintains its equivalence, so it's still true. So we're not changing anything here. We're kind of just rearranging the way it looks. And so we want to make sure our work always looks the same. We're going to add it on both sides. Well, a plus 5 and a minus 5 give you 0, so we can just get rid of them. So 2x equals 6. And now if I want to get x completely by itself, we want to reverse this. This says 2 times x. So if I divide by 2, that eliminates it. If you think about it like a fraction, 2 over 2, it just becomes a 1x. So it's just x. And 6 over 2 is 3. Now you could go back and check it, plug it in. 2 times 3 is 6, plus 5 is 11. That's what we want. All right, so this equation has an answer of 3. Let's go ahead and check this one. And if you notice, it looks very similar to what we ended up with halfway through this one. So again, we're trying to get x by itself. We're dividing by 2 in this case again. And x equals 3. So let's answer the question. Are these equivalent? Yes. And then it does say explain, and that's always important. Can we explain? So they both have the same solution. And what is that solution? X equals 3. All right, so just a little more practice solving these equations. Let's make sure that we remember all the little steps that we need to do for different situations. And then can we also show a check? So real quick, let's kind of reinforce those old skills that we had. So if I want to solve this, I'm trying to get x by itself. Here's my dividing line. The 27 and the 5 have to go. So since this is a minus 27, I'm going to add 27, leaving me just 5x on the left side. 40 on the right side. This is multiplication. To undo multiplication, I'm going to divide. And so x equals 8. Now I'm going to show a check. Check is important. If I can plug this back into the original equation and both sides come out equal, then I know my answer is right. So going back to 5x minus 27 equals 13, replace x with the value that we think is the solution, and then simplify both sides. The right side's already simplified. It's going to stay 13 the whole time. And we're just going to go ahead and walk through the simplification process of the left side. And we do end up with 13 equals 13. So I know my answer of x equals 8 is correct. All right, jumping over here. Now we're not going to add first here because if we add 11 to 11, we get 22. We want it to go away so that x ends up by itself. So to go away, we basically need it to get to 0. So when I see a plus 11, I'm going to minus 11. That eliminates it. So I have 4x equals 32. Now I'm going to divide by 4, because again, this says 4 times x. 4 over 4 is a 1x. 32 divided by 4 is 8. So if this for sure is x equals 8, and we'll check it to make sure, then these would be equivalent equations because they have the same solution for x. So let's check it and see if that's true. So our original, 4x plus 11 equals 43. Plug in our answer of 8 and simplify both sides. Right side is simplified, so we leave it 43 the whole time. Both sides come out to 43. My check is good, which means my answer of x equals 8 is good. So therefore, these are equivalent equations. Now, what happens when I see this? So I still want to take care of, we used to call it the lonely number, so we want to take care of this first. Technically, you could multiply everything by 6, though. We're going to multiply by 6. If you wanted to multiply everything by 6, right now you could. So we'll take a look at that in a second. But the best thing to do is to get rid of the 7 first. Now, I minused it because I saw a plus. So I have x over 6 equals 4. And then at this point, this says x divided by. So I want to multiply by 6. Now think about why. If this was 6 over 1, and I multiply, I'm going to end up with a 6 over 6, which is a 1x. And that's what I want. So if I multiply by 6 on this side, I got to multiply by 6 on this side. And I get my answer of 24. So let's check it. So I am going to start with my original. And then replace it. And then run the numbers all the way out. 24 divided by 6 is 4. 7 plus 4 is 11. Now, we talked about if we started with this, so go ahead and rewrite it. We said we could actually multiply first. If I want to get rid of this 6 underneath the x, I need to times by 6. I'm allowed to do that. Now, we always talk about getting rid of the lonely number first. That's a best practice. You don't have to do it. We usually don't divide first because if you divide a lot of numbers by 5, you get nasty decimals. So why create them? Let's subtract first and then divide. In this case, we're multiplying. So if you're multiplying, you're not going to create a nasty number. So I can multiply this entire side by 6, and I can multiply this side by 6. Let's see what happens. So when I multiply the x times 6, again, think of it as 6 over 1. That's going to eliminate that. So I have just x. If I multiply the 6 times the 7, that's 42. And 11 times 6 is 66. Next step would be subtract 42 from both sides. So x is by itself. And take a look at what I get. I got the same answer. So as we get into more and more sophisticated algebra problems, it's okay and it's actually a really good thing to be flexible. You don't have to always do things the same way. There's times that there's an advantage to doing things differently. Okay, so we always add or subtract first is not a rule that you have to hold by 100% of the time. It is a best practice, but there's situations that you may want to actually multiply depending on what's going on. So I want you to see that you are allowed to. You also could divide first. The only reason you'd ever want to divide first is if every single number divided nicely, though. So since you see a 4 here, if this was, say, a 12 and this was a 40, and those both divide nicely by 4, then you could go ahead and divide everything by 4 and get rid of this and work your way through it, and that would be perfectly fine. But for the most part, usually it's not set up to perfectly divide all the numbers into whole numbers, so we don't do that. Okay, but it is important to understand that there's not one way to do this. There's multiple ways to accomplish these goals. All right, let's flip it over. Real quick, they're going to show you some visual representations with these scales balancing each side. And it's kind of important to just understand what it looks like, because you could see this anywhere, and it's important to understand how this relates to your equations. So if this is balanced, it means it has the same amount of weight on both sides, which means they are equal. And so these are all ounces. OZ equals ounces. And so if I look over here and I counted them, I've got 4 and 4 is 8 plus 3 more. I have 11 ounces on this side of the scale. This side only has 3 ounces, and it also has 4 x's. So what we want to do is we want to kind of represent this as an equation. So visually, both sides are balanced. We want to figure out, what do these x's actually represent? How many ounces each? Okay, so if I write this equation, 11 equals 3 plus 4 unknowns. We don't know what those are. So the unknowns are your variable. And so we're just going to call it x. We would solve for this. So of course we're going to minus 3 on both sides. Again, you could divide by 4, but why would I want to divide by 3 by 4 and 11 by 4? I don't. So I'm going to get 8 equals 4x. Divide by the 4, and x equals 2. So it says write and solve an equation for each of the scales below. So what does this mean? Each box with an x is worth how much? 2 ounces. If this scale is balanced and has the same amount of weight on both sides, there's 11 ounces here. So I need 11 ounces over here, which means each one of these doesn't weigh 1 ounce like these other ones. They must be 2 ounce blocks. 2, 4, 6, 8, 9, 10, 11. If the scale sits flat, they're balanced. So each one of these represents 2, and we solve the equation to get there. So let's try one more, sliding down. So right here we have 1 ounce, so 1, and we have 3 of these x's. And over here, 1, 2, 3, 4, 5, 6, 7 ounces on that side. And since it's balanced, I know this is my equal sign. So if I'm going to quickly write an equation, I have 1 ounce plus 3 unknowns. I don't know how much those weigh. Okay, but since they're all labeled x, we know they're all the same amount of weight. And on the right side, I have 7 total ounces. Solve the problem. We could divide by 3, but why would we want to? It's going to create some nasty numbers. So I'm going to subtract 1 on both sides. 3x equals 6. Divide by 3. X equals 2. And so again, each box labeled X is worth 2 ounces once again. So it's kind of just a visual example of how these equations work.